Okay, we'll begin recording here. So, polar coordinates. Up to now, you have used rectangular coordinates. Rectangular, like in calculus, in pre-calculus, in algebra, you have an x and a y, variables x and y. But sometimes for certain types of areas, rectangular coordinates may not be convenient. And so, like it says here, polar coordinates offer an alternative way of locating points in a plane. They are useful because for certain types of regions and curves, polar coordinates provide very simple descriptions and equations. The principal applications of this idea occur actually in multivariable calculus, the evaluation of double integrals, and the derivation of Kepler laws of planetary motion. Okay, so if you, how many have to take multivariable calculus, Math 280, okay, a number of you here, and very good. And so you will be seeing this again, certainly. And it comes up in other courses as well. But, all right, so let's talk about this, curves in polar coordinates. Okay, now there's a lot of writing here. I just want to get to some pictures here. And I don't know why that keeps popping up. Please don't pop up. Good. Okay, so a polar coordinate consists of an angle and a radius. So you're used to rectangular coordinates. So give me an x coordinate, give me a y coordinate. I'll locate a point in the xy plane with that x coordinate and y coordinate. But with polar coordinates, you have an angle theta that's measured from the positive x-axis, okay? And then along that, using that angle theta, you move out from the origin a certain radius, and you get a coordinate r theta. That's what a polar coordinate is. So instead of x and y, you have a radius r and an angle theta. Radius, like for circles, is always measured, well, let's just talk about a circle, you know, that's centered at the origin. You measure the radius from the origin. It's the same here with the polar coordinate. You measure your radius from the origin. Now, we can also, oddly enough, we can have a negative radius. They mention that here. We can extend the meaning of polar coordinates. And let me see here. Let me just highlight this here. Okay, we extend the meaning of polar coordinates in the case in which we have a negative radius. Okay, and by agreeing that the points negative r theta and r theta lie on the same line through the origin at the same distance, absolute value of r. So you see, and again, you know, we can, you know, I think the pictures are extremely helpful looking at the pictures. So you see, you have an angle theta there, and then you move out a positive radius. You move forward a positive radius, and that gets you to r theta, the point with polar coordinates r theta. But if your radius is negative, you don't move forward, but you move backwards that value, that radius value. And so you have another polar coordinate that has a negative radius and an angle theta. Okay, so if the radius is positive, you move forward. If the radius is negative, you move backwards. Okay, I always think of Michael Jackson, the singer, right? When he did his dancing, sometimes he moved forward, sometimes he moved backwards, right? So that might be before most of you. But how many have heard of Michael Jackson? I'm just curious. I won't. Oh, good. Okay, he was very big when I was a teenager. Very big. Okay. So let's look at a few examples here. Okay, so in example 1, they want you to plot the points whose polar coordinates are given. Now, like for A, you have 1, 5 pi over 4. So 1 is the radius, and 5 pi over 4 is your angle. Now, it always helps to convert angles into degrees. So we know pi is how many degrees? How many degrees is pi equal to? 180 degrees. That's right, Renaud. So if you take 5, so for example 1a, if you take 5 and multiply it by pi and divide by 4, that's like taking 5 times 180 degrees divided by 4. Hence, you get 225 degrees. So how would we plot that polar coordinate? Well, let's look at the figure below, figure 3. Okay, so, and it's, you know, you can follow in your ebook, but I think it's, I think you can see it here. So you see there figure 3 on the left, from the positive x-axis, they draw an angle of 225 degrees or 5 pi over 4. And then looking in the direction of 225 degrees, they move forward a radius of 1. Let's look at B. B has a polar coordinate 2 pi over 3, or 2 comma 3 pi. Well, 3 times pi would be how many degrees? For this example 1 part B, 3 times pi is how many degrees? Pi is 180 degrees. So 3 times pi would be how many degrees? That's right, Jacob, 540 degrees. Now, how many degrees does it take to do one like revolution in a 360 degrees? Right, that's right. So 540 degrees would be like doing one revolution, which is 360 degrees, and then half another revolution, which is 180 degrees, because 360 degrees and 180 degrees makes 540 degrees. And that's what you see in the second picture there. You see they rotate out an angle of 3 pi or 540 degrees in figure 3, the second picture, and then looking in the direction, pretend like you're looking in the direction of the angle 540 degrees. Looking in that direction, you move forward. Move forward a distance of 2. Okay. Are there any questions on the first 2 pictures there in figure 3? Please let me know. All right. All right. Well, let's move on. Let's move on. For C, we have polar coordinate 2, comma, negative 2 pi over 3. Well, now 2 pi over 3 is 120 degrees. So negative 2 pi over 3 would be negative 120 degrees. And in the third picture, you know how to deal with negative angles. Instead of going counterclockwise, you go clockwise. So you go clockwise 120 degrees, and then you move forward a radius of 2. And then finally D, now D, that polar coordinate, you have a radius of negative 3 and an angle of 3 pi over 4. Well, 3 pi over 4, that's 3 times 180 degrees divided by 4. That is 135 degrees. So you see there on the fourth picture in figure 3, they do an angle of 135 degrees. But then you don't move forward 3 units, you move backwards 3 units. And that gets you in the fourth quadrant. Okay, so this is how you you plot polar coordinates. Are there any questions on example 1? Okay. Well, now, it's natural to be able to take rectangular coordinates and convert them to polar coordinates, or to take polar coordinates and convert them to rectangular coordinates. And so you remember from your trig days, you remember that the cosine of theta is x over r, and the sine of theta is y over r. Okay, you have your uh, first, second, third, fourth quadrants, and like in Figure 5 here, you have a Cartesian coordinate x, y, and but for that Cartesian or rectangular coordinate x, y, but for that coordinate, then there's a certain angle and a certain radius that will get you to that same point. Okay, well, so the connection between polar and rectangular coordinates is then, of course, what you see here, and then naturally, x equals r cosine theta and y equals r sine theta. How many remember those formulas from their trig days, when they took trigonometry? Okay, Jacob and Renaud and Tull and Marcus Mapping, and sure, Now, of course, you'll have access to this on the final exam, right? These formulas, but you really should know them, right? You really should know them. Few more things too. We mustn't forget. That with hold on here. Yeah, with rectangular and polar coordinates. X squared plus y squared equals r squared, right? And the tangent of theta is equal to y over x, right? And so, again, there's that standard picture there. You have that right triangle. So of course, x squared plus y squared equals r squared. That's the Pythagorean theorem. And then the tangent of theta is opposite over adjacent. So tangent of theta would be the y value over the x value. Okay, so we know that. And so, we have some fairly simple problems here. In example 2, they want you to convert the polar coordinate 2 pi over 3 into Cartesian coordinates or rectangular coordinates. And easy enough, x equals r cosine theta, y equals r sine theta. So it's, easy. Okay, and now naturally in polar coordinates, just like with like Cartesian coordinates, x and y. I'll say Cartesian because they're using Cartesian here. Cartesian coordinates, x and y, you have graphs, right? Like y equals x squared, that's a parabola. You can write y as a function of x. Well, oftentimes with polar coordinates, we want to, where we have r and theta as our variables, and we want to write r as a function of theta. And so, we can do that. We can do that here. So like in example 4, they ask what curve is represented by the polar equation r equals 2. Okay, well, in the solution, the curve consists of all points, all polar coordinates that have a radius of 2. So theta can vary, but the radius is always equal to 2. And so if we were to plot a graph in Figure 6 of r equals 2, we would get a circle centered at the origin. Okay, we would get a circle centered at the origin. Okay, let's look at a few more. Let's look at it. Are there any questions on that? Okay, let me ask you this. You go to the whiteboard real quick. So if your polar graph is r equals 2, what would your graph, how would we write that in terms of Cartesian coordinates? Well, let me show you how we do it. If r equals 2, then r squared equals 4, right? But what is r squared equal to in Cartesian coordinates? So x equals r cosine theta, y equals r sine of theta, and x squared plus y squared is equal to r squared, right? So r squared is x squared plus y squared. That equals 4. So here would be your equation in Cartesian coordinates. A circle of, what's the radius of the circle? That's right, Renaud, circle of radius 2, centered at the origin. Okay, so you grew up with this. X squared plus y squared equals 4. Hey, that's an equation of a circle of radius 2 centered at the origin. But now, in terms of thinking about polar coordinates, a circle of radius 2 centered at the origin would have the equation r equals 2. So we have to start thinking now in terms of these polar coordinates. In example 5, they say sketch the polar curve given by theta equals 1. All right, well, so there, if theta equals 1, you're allowed to let the radius be anything, right? There's no restriction on the radius. It's just all the points on your polar curve have to have angles of theta equals 1. So if we were to graph that polar curve, this would be what it looks like in figure 7. Okay, every one of those points on there, okay, and those red points, 1, 1, 2, 1, 3, 1, those are in polar coordinates. Okay, the first value is the value of the radius, but the angle theta is always equal to 1. And then going downward, you have polar coordinates -1, 1 and -2, 1. Okay, are there any questions on that? Please let me know if you have any questions so far. And I am glad, there are, attendance is really important now, and you're here, so that's good. That's good. Okay, that's good. All right. All right. So well, let's continue on. Now let's look at something a little more complicated, I guess. What if you had the polar equation r equals 2 times the cosine of theta? R equals 2 times the cosine of theta. Well, you want to find a Cartesian equation for this curve, right? So, well, and you want to sketch the curve. So how would we do that? Well, this one's kind of complicated. So we have to plot a bunch of points. So just like when you learned about how to graph like a parabola, y equals x squared. When you learned that and it was new, what did you do? You picked some different x values, usually nice x values like 0, 1, 2, -1, -2, and then you found the y coordinates for those x coordinates and then plotted the points and drew the picture of the parabola. It's no different here with polar coordinates. You pick nice values for theta, and then you compute the radii for all those different values. So like when theta equals 0, the radius is 2. So that means the polar coordinate is 2, 0. So do you see there in the polar graph, the red polar graph on the right, how they have the coordinate 2, 0? Give me a thumbs up if you're seeing that. Okay, Renard's seeing that, and Todd and Leping. And you notice they don't have an XY axis there. It's just, you're plotting the angles and radii. Good, thank you, people who answered. And okay, at pi over 6, if we do 2 times the cosine of pi over 6, well, the cosine of pi over 6 is √3 over 2. So 2 times √3 over 2 is equal to √3. So the polar coordinate is √3 pi over 6. So you from the x-axis you go up an angle of 30 degrees, and then from the origin you move out a distance of √3, and that gets you to that polar coordinate. When theta is pi over 4, the radius is √2. So √2 pi over 4. You do from the positive axis. You go out an angle of, that is the x-axis, right? Of course, but that you see there. But let's just, we know we draw angles from that positive x-axis. Pi over 4 is 45 degrees. You draw 45 degrees, move out square root of 2, which is like 1.414, and you keep doing this, and eventually, like at that pi over 2, well, there you're looking upward, an angle of 90 degrees, but the radius is 0. So 0 pi over 2 is right at the origin. And then you start getting negative radii. For 2 pi over 3, which is 120 degrees, the cosine, 2 times the cosine of 120 degrees is 2 times -0.5, which is -1. And so there you look in the direction of 120 degrees, but move backwards -1. Okay, and then you get more negative angles, and then finally when you're at the angle of pi, 2 times the cosine of pi is equal to -2. So you look in the direction of 180 degrees, but you move backwards 2 units, and that gets you back at the point 2, 0. Okay, so that's how you graph. That's how if you found all the little individual points, that's how you would graph a polar curve. Are there any questions on that? And back, of course, when I was in college, this is how you had to do it. This is how we had to do it, and it's fine. But of course, you have Desmos to help you. So let's go to Desmos, and I'll show you how to graph this polar graph. Okay. How many want to see what Desmos can do? Okay. Wow. A lot of hands up on that. Okay. All right. So, and of course, you will have the Desmos graphing calculator available to you on the final exam. Let us see here. So I want to share Desmos. So we're working through this example here, example 6. We're working through example 6, plotting the polar graph r equals cosine of 2 theta. Okay. Give me a thumbs up if you're seeing Desmos okay. Okay, thank you. All right, so all you need to do, it's really quite simple. type in R equals 2 times the cosine of theta, and there is your graph, and theta goes from 0 to 2 pi. Or 0 to pi. In other words, to complete this graph, this polar graph, you don't need to go out like to 2 pi. You can go out to pi. And naturally, we can make our axes, you know, a little, let me see, one moment here. Let me just try to, you know, have a good, and notice I have radians selected, right? I have radians selected. There we go. Okay, so there is your polar graph. There's your polar graph. And, you know, I like the TI calculators because when you graph a polar graph, you can, you know, depending on what your scale is for theta, it'll graph it slowly, and you can see it actually graph it. But it's fine. Desmos is fine. I have a 1 here. I don't want a 1 here, right? Okay. Let me, while we're at it, just so you can see this. What if we had the cosine of 3 theta? Well, first, are there any questions? Are there any questions on this? By the way, this polar graph looks like a circle of what radius? R equals cosine of theta appears to be a circle of what radius? Radius 1. Good. And that's right, Leping. And where's it centered at? What's the center of this circle? Where does the circle, what's the center of the circle? It's not the origin. It's 1, 0. That's right. Okay, so you can see that from the x-axis and the y-axis. And normally in the polar graphs, I mean, sometimes they show, you know, we know what the x-axis is and the y-axis. It's there in the picture, you know, but sometimes they don't label the x and y-axis. But so anyway, we have a circle of radius 1 centered at the coordinate 1 at the at the Cartesian coordinate 1, 0. So let's go back to the example here. We're looking at this example 6. Okay, and now it wants you to find a Cartesian equation for this curve. Okay, so we'll go down a little bit here to part B. And to convert the equation, the given equation, the polar equation, R equals 2 cosine theta, into a Cartesian equation, we're going to remember that if, you know, since x equals r cosine theta, cosine of theta is x over r, right? So r equals 2 cosine theta becomes r equals 2x over r. Okay. And so, let's see here. Maybe this would be better. I mean, it's fine what they have here, but maybe I can work it on the whiteboard too. Let me go to the whiteboard. So, example 6. Write the polar equation r equals 2 cosine theta as a Cartesian equation. So r equals 2 cosine theta. But for our Cartesian equation, I want x's and y's as my variables. So, okay, well, cosine of theta is x over r. So I can replace cosine of theta with x over r. Now, this means then that r equals 2x over r. But what I can do is I can manipulate this equation and multiply by r on both sides. And if I do that, I'll get r squared then equals 2x. That's fine. But what is r squared equal to? What's r squared equal to, class, in trigonometry? Cosine of theta is x over r. Sine of theta is y over r. That's good. Good, Renaud. Good, Leping. X squared plus y squared equals r squared. So r squared is x squared plus y squared. That equals 2x. All right. So, well, all right, if x squared plus y squared equals 2x, that means x squared minus 2x plus y squared equals 0. Okay, so at this stage, what am I going to do? What am I going to do here to get this to, you know, I want a circle that whose center is 1, 0 and has radius 1. I want to get the standard form of a circle. So what do we have to do here? I need a little space, so let me get a little space here. Takes a while to erase, doesn't it? That's okay, we'll get there.
X minus y squared.
Completing the square, good. Good, Leping, very good. So x squared minus 2x. I'm going to add something here to the left side of the equation. But if I add to the left side of the equation, I have to add the same number to the right side of the equation. Okay, and so that's right. Good, Renaud, we're going to add a 1. You can review completing the square. We're going to add a 1. Basically, you take the negative 2, the coefficient of x. This is so long as the coefficient of x squared is equal to 1. You take the negative 2, the coefficient of x, divide it by 2 and square it. That'll get you negative 1 squared, which is 1. So you're going to end up with x minus 1 squared plus y squared, which is y minus 0 squared, equals 1. So the center is 1, 0, and the radius is 1. Are there any questions on that? Okay. Okay, so that is example 6. Now, so if I go back to example 6, then you see they leave out, they just say, you know, completing the square, we obtain there. And, you know, they left out a few steps, but that's because they know you can fill those steps in. Okay. Now, another way you can look at this, another way you can look at polar coordinates is you can, you know, like in example 7, they want you to sketch the curve r equals 1 plus the sine theta. Now, normally, I mean, I think many of you will be utilizing Desmos. Okay, but still it's important for you to make a connection between the graph of r equals 1 sine 1 plus sine theta, like you learned in trigonometry, and then the polar graph. So if you notice here, the graph r equals 1 plus sine theta is going to be what's called a cardioid. Okay, and so figures 10 and 11, they draw r equals 1 plus sine theta like you learned in trigonometry. Well, you would normally write y equals 1 plus sine theta, but they draw r equals 1 plus sine theta in figure 10 here. They draw that, and they graph that trig function. So it's the sine wave lifted up by 1 unit, right? That's called a vertical translation. How many remember that from their trig days? Taking trig functions and moving them around, and okay, good. So you see, if you look at that graph then of r equals 1 plus sine theta, you can actually follow the graph in figure 10 there, and then plot polar coordinates and generate the polar curve r equals 1 plus sine theta. So like the graph starts out with a radius of 1 and an angle of theta equals 0. Okay, but then when you get to like an angle of pi over 2, if you look at that graph above in figure 10, when you know the radius, what's it do? What's it do from 0 to pi over 2? Does the radius, based on this graph in figure 10, okay, does the radius increase or decrease when theta goes from 0 to pi over 2? That's right, Renat, it increases. The function's going up, right? So if you look at the polar graph then below, from theta equals 0 to pi over 2, the radius keeps getting larger. It keeps getting larger until it reaches a maximum of radius of 2. But then what happens in figure 10 above when your angle goes between pi over 2 and pi? What happens to well, actually from pi over 2 to 3 pi over 2, what happens to the radius? Does it increase or decrease based on the figure 10 there? What do you think? Renat has a thought. From pi over 2 to 3 pi over 2, what is the function doing in figure 10? Is it increasing or decreasing? It's decreasing. That's right, Jacob. And so because it's decreasing, if you look then on B there, on B, well, actually B and C, from pi over 2 to 3 pi over 2, the radius decreases. And then at 3 pi over 2, the radius equals 0. But then from 3 pi over 2 to 2 pi, the radius increases. And so in part D, you go from 3 pi over 2 to 2 pi, the radius increases. And you get a cardioid. So this is like making a connection between the graphing that you learned in trigonometry and polar and graphing a polar curve. And you know, again, I know you're going to be using Desmos to help you, but there's nothing wrong with you know, I mean, it is an important skill to be able to take some graph and then figure out which polar curve it goes with. And you'll see a problem like that in your homework, and could even see it on the exam where they just give you a picture of a graph of some, you know, a trig graph, like in figure 10, and then you have to find the correct polar curve to go with that, like you know, and they would provide like 3 or 4 polar curves, and you'd have to find the right one. Okay, so that would kind of force you to, you know, just show good understanding of this, or decent understanding. They even have, like in if you go down here, the curve r equals cosine of 2 theta, they graph that also in figure 12. And then you see they have sections of the graph, 1, 2, 3, 4, 5, 6, 7, and 8. And then they graph those sections in the polar curve in figure 13. Okay, so based on, I'll try to have it show, I made it a little smaller in the window here, so hopefully both will show. Yeah, this is how, you know, I mean, that's, you know, doing it, working it out, but it's actually not that hard. You know, it kind of saves you from plotting a lot of points if you just look at the trig graph and the, and then use the trig graph to help you trace out the polar graph. Now, if you were to use Desmos, r equals cosine of 2 theta, if you were to do that, then in Desmos, cosine 2 theta, whoops, I got to change my window. Let me go from -3 to +3, and from -3 to +3. Okay. That's a 4-leaf rows, class. 4-leaf rows. Okay. Are there any questions on this?
I know that is a quatrefoil.
What's it called? A quatrefoil?
Quatrefoil, yeah.
Okay, yeah. Maria says it's a quatrefoil. I mean, I used to it being called a 4-leaf rose, but sure, quadrifoil, and you can do all kinds of things. You know,
You
can
see
do
them all over the place.
You see them all over. Okay.
Yeah.
Okay.
In
Well, yeah.
architecture and everything, they're all over the
Yeah.
place.
And suppose you wanted to find the area of that inside those leaves, those 4 leaves in the quadrifoil or the 4-leaf rose. Well, if you could find the area of 1 leaf, since they're all symmetric, they're all the same area, you could take the area of 1 leaf and multiply that area by 4, right? So, and that's something we're gonna talk about in section H.2. Okay, are there any questions? Any questions? Okay, let me stop the recording.